Hi, Assalamualaikum and good evening to all. Okay, today I will show you force method for frame by using the method of virtual work. Okay, before this we used a table to calculate or the delta and also the rotation, but now I'm going to show you uh, how to calculate, how to use force method for frame by using the method of virtual work. Okay, now. Okay, this is the overall view for frame. Okay, for statically indeterminate frame, you have two types, which is single story or unusual geometry, and the second one is multi-story. Okay, force method can be used for single story, and for high degree of multi-story, okay, you can use okay, slope deflection. You can use moment distribution, and also you can use stiffness method. Okay, stiffness method you will learn later with Dr. Wan Sabki. Slope deflection and moment distribution you have learned in your previous structural analysis course. Okay, I will go through example 9.5, and then you will see a better picture of how to use force method by using the method of virtual work. Okay. Okay, as you can see here, example 9.1. Okay, we have the saddle bench shown in the photo is used to support the bridge. Okay, bridge deck. Assuming its top is subjected to the loading shown as figure, we have 40 kilonewton here, distributed load. And then the question asks us to determine the horizontal support, which is AX. Okay, as you can see here, A is pin, B also pin. So you have AX, AY, BY and BX. The question asks us to find the horizontal support, which is AX lah. Okay. Okay. Step first, you need to calculate the degree of indeterminacy. R is equal to 3n, which is reaction now you have 4, AX, AY, BY and BX, and then 3n. N member is 1, okay? This one we calculate it as 1 member, frame attached to each other. And then 4 is greater than 3, so you will have 1 degree of indeterminacy. So you need to remove 1 unknown, okay? Okay, since this question asks us to calculate AX, so it's easy for us to just remove the AX. The one unknown, we remove AX. And because at last, we will get the value of AX. Okay. For primary structure, pin support at A being replaced with a rocker. If you want to remove the horizontal reaction, then you replace pin with a rocker. Okay, like this. Before this one is pin. Okay, and then now we replace it with a rocker, which is we only have AY, we don't have any more AX. At B, we remain the pin BX and BY. Okay, the 40 kilonewton is still there. Then for redundant structure, here, remove the 40 kilonewton. Once you remove the AX here, you need to add back AX here. Okay, see, the frame will bend like this. Okay, let's see for primary structure. You remove pin and you replace it with a rocker. You have 40 kilonewton here, and then push the frame downward, and then the deflected shape will become like the dotted one here, and this displacement and this support will displace like this, which is delta A. Okay, so that one is delta A. For this one, you add AX here. AX will push the rocker to displace here, which is the displacement here called as AX F A E. Okay, same concept like the previous example. Okay, now you are going to write the compatibility equation. Okay, step number 3. 0 is the actual, which is zero displacement. Delta A is from the primary, and AX FAA is from the redundant. Okay, this is your compatibility equation. Okay, to use the method of virtual work, you remember the formula is delta is equal to the integration from 0 to L M, capital M, small m, divided by EI dx. Okay, for those who forgot about virtual work, you can refer back to your textbook, and then you can see how to calculate the delta by using this formula. Okay, since you want to calculate the capital M, so I put it as step number 4. Calculate capital M first. Okay, refer to primary structure, because primary structure now are using the actual load. You have 40 kN distributed load on top. You don't have any AX because you have removed it. You have AY, BY and BX. Okay, calculate support reaction, meaning you need to calculate AY, BY and BX first. Okay, 40 kN here, multiply by the length 20 meter, then you will got 800 kilonewton. Okay, 800 kilonewton in the middle, automatically AY will become 400 kilonewton and BY will become 400 kilonewton. Okay, now you have 400 kilonewton here, and then you have 400 kilonewton here. You want to calculate capital M, meaning you need to cut the section at x1, x2 and x3. Okay, I will show you the calculation M1 first. This is your x1. This is your 400 kilonewton. You cut this section, yeah, and then you have your M1 here. So do summation moment at this point. So summation moment at there is equal to 0. Then you will have M1 is equal to 0, because we don't have any horizontal load here or here to multiply with x1. Okay, so M1 is equal to 0. Same like this section. So M3 also equal to 0, because when you cut here, this is your M3 and X3. This is 400. Okay, nothing can be multiplied with X3 to get M3. So M3 0. Then to get M2, you need to take this section. And then it become like this. Okay, this is your X2. And then you have 400 here. And then your M2. And don't forget about the 40 kilonewton on top. Okay, so 40 kilonewton you convert into the point load, 40 multiplied by x2. Okay, what you're going to do is you do summation moment here. Okay, here, summation moment here. Then you will have minus 400 multiplied by x2, and then plus m2, and then don't forget about this loading, plus 40x2 multiplied by x2 over 2 is equal to 0. Then you will have your M2, this value. Okay, you can try to calculate it. Okay, that one is capital M. Now we move to small m. Okay, small m here. Okay, you replace AX is a virtual 1 kilonewton. So automatically BX will become 1 kilonewton. And AY 0, BY 0, because we don't have any vertical load. You have 1 kilonewton here, you have 1 kilonewton here, and then you cut at the same x1, same x2 and x3. Okay, I will show x1. X1, you have 1 kilonewton, and then you have small m1. Okay, do summation moment at here. Is equal to 0. So you have this one, positive 1 multiplied by x1 minus m1 is equal to 0. So m1 is equal to x1. Okay, same with x3. Now I am going to show you the x2. Okay, this is x2. And then you have your m2. Okay, you also have 1 kilonewton. Okay, here. And then you can do summation moment here. This is 5 meter. Okay. Summation moment at dot is equal to 0. So you will have plus m2. Okay. Plus 1 multiplied by 5. So you have m2 is equal to negative 5. So this is 1. Okay. You have m1, m2 and m3. Then step number 6, you need to calculate delta. The formula is this one. Okay. From 0 to L is for x1 is 0 to 5. This is x1, 0 to 5, 5 meter. This is 20 meter. And this is 5 meter. Okay, so 0 to 5, this is capital M1, small m1. Okay, capital M1 is 0, small m1 is 1. Capital M2 is this one, small m2 is negative 5. And also same for 3, m3. Okay, you solve and then this is your delta E. For FAA, the formula is m multiplied by m but small m only. So you have x1 squared minus 5 squared, x3 squared, then you will have this 1. Okay. Okay, this is your delta A, this is your FAA. Remember you have this equation. You plug in this value here, and then you plug in this value here, and then you solve it, then you will get AX is equal to 229 kilonewton. Okay, this is method of virtual work. It's quite straightforward and clear. If you use table, it seems like you are not so confident with the answer, with the negative and positive value of the table. If you want to be sure, you can also use method of virtual work for beam. This one I show is for frame, similar. Okay, the difference is just the structure. Okay, thank you. We will continue with another video for another example. Okay, thank you. Bye-bye.